So welcome everyone to today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today we're going over an application-focused webinar, taking a look at thermal conductivity testing of concrete and building materials. So kind of going right into it here. For those that may not be familiar, concrete is one of the most consumed materials on Earth. It is used in a variety of different applications. There's a lot of considerations going around in terms of its overall thermal performance. You can kind of see a graph here, the impact that it's actually having on the environment. So we'll actually be talking about not only just general concrete, but some of the more, we'll say, bio-based alternatives that are kind of trying to combat some of these negative issues that the general production of concrete is essentially causing in the world. So yeah, 950 tons of concrete are produced every second, which is kind of hard to imagine. I tried to represent this in a way that, maybe you'll be able to pick up a little easier, but, that's a significant amount of elephants, to put it lightly, right? So just, the scale and the volume of material being produced is quite significant. And we're going to go through some of the different considerations and how to best test this very utilized material in today's session. Now, the reason, of course, why there's so much of it being used is because it's everywhere, right? It is in the fundamental infrastructure, in the construction of the buildings, the bridges that we, use every single day. Some of the larger structures existing out there, like some of the dams and, filtration and water systems. Concrete is, highly utilized in this space. But with that comes a variety of thermal considerations, sometimes specifically related to the use of the application space. Sometimes it's more so used to help quantify the mechanical strength or the tangential relationship between the thermal and mechanical properties. But in terms of the thermal performance and really why thermal conductivity matters here, it's dependent on what your goal is. There are some applications, in certain building systems where you're actually trying to improve the insulative performance. The building envelope, the concrete can act as a means of insulation to help, with the building efficiencies, keeping heat in. So in this case, you're actually targeting a lower thermal conductivity as your primary performance metric. But there's also areas where you're trying to remove the heat or get the heat out. Again, this can be, under considerations for, thermal cracking under loads, some of the heat islands that have been, I've seen some publications on that recently talking about how all this heat is building up in many of these urban infrastructures. So ways to actually remove the heat here, you'd be targeting a higher thermal conductivity. And in either case, together with those two, the conditions that the material is subjected to, whether that's hot or cold environments, moisture and saturation, these different variables will impact your effective performance. So being able to quantify your material under those conditions is going to be really important. And again, something that we'll talk about here today. There's actually also a few very specialized use cases for concrete, some of which we'll be talking about here today. But these are just a few examples related to some clients that we've recently worked with or have worked with in the past. Everyone is currently talking about the AI data centers and all of the construction that's going to be going on. There's actually some very interesting work that I've seen looking at, again, more of the conductive concretes in this space to almost act as a form of thermal management to help remove some of that heat inside of some of those buildings. Nuclear infrastructure, specifically for like waste and long-term storage management. Oftentimes concrete is, a key component in these builds. And in these considerations, the lifetime expectancy and performance can ultimately be quantified and modeled based on some of the thermal considerations. And lastly, as I kind of mentioned at the very beginning, they're bio-based materials. So these bio-based alternatives like hempcrete, trying to find more naturally occurring, less environmentally harmful alternatives to either replace or help at least offset some of the more traditional concrete use. Again, coming back to those green and environmental initiatives that are out there. So we'll be talking about some of these as we go through today's session. But really, the content here is really focused on the thermal data, but it can really lend itself to a few different areas depending on where you're coming from. So maybe if you're on like a formulation or a mix designer who is dealing with, the different additive mixtures, the aggregates, the binders, trying to find that, we'll say, perfect recipe to meet the performance needs of your product. Engineers who are potentially looking at modeling some of those larger infrastructure builds, the thermal stresses as it relates to the heat buildup and heat management in some of these infrastructure systems. And then more generally, just, testing and quality control and certification groups. Like, how do I best test these materials that are coming through that need to have a stamp of approval in terms of their performance rating? So these are a few of the different kind of topics and focuses that we'll go through with today's content. But I thought I'd maybe start with a quick poll here, just to get some kind of feedback from the audience. Where is your interest in thermal conductivity coming from in this space? I think we've kind of had a few options like general material performance, academic, bio-based, or maybe some others that we didn't think of initially. So I'll leave the poll up for maybe another 10, 20 seconds or so, give the folks on the line an opportunity to answer, and then we'll kind of take a look at the results here. All right, I see actually most of the audience has answered, so we'll go ahead and end the poll here. And yeah, actually just kind of to share the results. So yeah, it looks like, a good mix, mostly coming from academic backgrounds and academic interests. We have some general material, some bio-based, and some others. To the folks that are in the other space, as we're going through the Q&A today, if there's any information on like where that application space is, I'd be definitely interested in knowing. Definitely feel free to kind of include that in your questions, like where your interest in this material performance lies. So thank you everyone for contributing there. I'll go ahead and stop sharing at this point, and we will get moving forward. So in terms of an agenda today, I'm going to start out with some general challenges in testing concrete, some different considerations to keep in mind as you go through the options that exist out there. I'll introduce C-Therm and specifically our Trident instrument for the testing and a lot of the data, of course, that we're going to present here today, which will lead into different application as well as some published work data over the through the use of these transient methods for thermal characterization in this space. We'll wrap up with some conclusions, and then, like I said, towards the end, we will have a group Q&A to go over any outstanding questions together. Okay, so starting out here, what are some of the biggest challenges when it comes to testing concrete? So, I put the picture here and you might say a little exaggeration, but I've done quite a bit of work with concrete over the last couple of weeks. And I can tell you the prep requirement can be something that really does bog down the testing time here, the actual effort, but it varies by method. So where the time will go is typically if you have to do any cutting or machining or planing, leveling of the samples, drilling. In the case of the image you can see on screen for kind of the use of a needle style sensor, having to drill the sample, apply thermal grease. Ultimately, these aspects introduce some challenges in how we get the samples ready as it relates to really your throughput capabilities. Also, the note here that in some cases, the prep can be destructive in nature to the sample. For some folks, that may be a significant factor to consider, especially I noticed a lot of folks from the academic side of things. If you are producing maybe only a handful of these R&D samples for testing, I know many times you're trying to get as many measurements out of it as you can. And of course, if you're going to go through a destructive process for a specific test, well, then you're going to have to produce more of that material for measurement. So talking about the different prep requirements and some of those throughput aspects will be a key focus for some of the data that we'll talk about coming up. But I mentioned steady state here, and of course, C-Therm, we focus on the transient class of measurement, but I did just want to take a quick minute to address general steady state considerations here for the groups that may be working in that space. So if you're unfamiliar, steady state systems typically have a dual plate style design where your sample is placed in the middle and heat flow is measured through the system under stabilized conditions. So you get thermal conductivity. You also hear of thermal resistance, or R value, as being referenced oftentimes as a performance output. Again, if you're unfamiliar, thermal resistance is just the thickness of the material divided by the thermal conductivity, which can also be standardized to specific thicknesses. Very common for different kind of construction. You'll see it referenced for like various insulation type samples as well. So certainly kind of one way about doing it. But for concrete, some of the issues come up in that, again, that prep in terms of the sample itself. If you don't have a very nice planar, even surface on both sides, what you'll typically run into in these dual plate style arrangements is contact issues, errors in that thickness determination, all of which will impede really what the heat flow measurement is trying to do. And this has a cascading effect, of course, on your outputted results. So again, we won't focus much more on steady state in today's presentation, but it is a challenge that I've seen some groups echo in the past, and just wanted to share that with you guys here today. Another area that is really worth considering as you're going about your testing here is looking at the level and the scale of the material that you're testing as it relates to its heterogeneity. Concrete, these types of samples, whether it be, just looking at traditional concrete with the porous aggregates, some of these more porous or aircrete style samples, or again, those bio-based alternatives, the scrutiny on the measurement in terms of what it's evaluating is going to be something to keep in mind here to make sure that the data that you're collecting is really representative of that sample. So the measurement system or the probe or the instrument has to be able to sample a significant enough volume of material to provide representative data on your sample. And again, we'll go through some basically data sets that show some of these different considerations in the coming slides. And lastly is the representative conditions. So I would say for thermal analysis, your environment is going to be a factor in any application. But of course, here we could look at a few kind of standouts, the temperature at which you're testing the material, the porosity that the material is. Like, are you in your preparation or sample formation going to be densifying the sample, or is it more of a loose, again, aerated system? And the temperature as well as the saturation levels will, of course, have an impact related to some of these other factors as well. But ultimately, being able to set up your material and test it in an environment that represents that end use application or end use condition is going to be critical to getting data that really provides a benefit to you. Because if you're not testing it in a way that it's actually being used, it's not really an apples to apples comparison. So we'll again highlight some examples of this through the coming content here today. So at this point, I'll kind of pause and just give a little bit of a background to C-Therm and specifically our Trident instrument. So for those unfamiliar or maybe new to C-Therm, we're a global leader in thermal conductivity instrumentation, really specializing in non-destructive thermal analysis solutions. Our goal and real purpose of what we do is to simplify thermal conductivity testing for the materials of tomorrow. This is done through the advancement of transient-based measurements. Our Trident instrument is our core platform that offers 4 different methods for thermal conductivity testing, really depending on, again, the type of sample, the size of the material that you have available, or again, the conditions you're looking to test under. This can all dictate which method is most appropriate. We're again going to go through that here today and talk about that as it relates to the concrete samples. This quote here from Abraham Maslow is one that we reference really in kind of the idea behind Trident. It really embodies that, that the idea very well, and that when all you have is a hammer, everything looks like a nail. So, one of the biggest sources of frustration and issues in terms of measurements is when you take a device or an instrument that is maybe very good at one sample type or one specific application, but not really designed for another, and then trying to force it to work. Really, we advocate for more of a toolbox style approach to really pick and choose the best option to address the task at hand. So for those that may be looking for additional information on kind of broader thermal characterization options, additional information on the methods available on Trident, we do have a method selection guide, which was recently updated a little over a year ago now, but it really covers off quite a lot of information on different methods for transient thermal conductivity testing, as well as steady state and some of the other more novel instrumentation types that exist out there. So whether you're new to conductivity or you're just looking to kind of catch up on what's kind of the latest and greatest out there, this is a great free resource to take advantage of. So moving on here now to kind of looking at some of the data, right? So thermal conductivity testing on these materials, what do the results look like? But before that, a common question maybe many of you are interested in is, well, what's the best method for testing concrete, right? Like what should I use to test by material? And to answer that, really, there's 2 core options that we will typically recommend or see used in this industry, but each come with different considerations. And again, we'll go through some of these, but one option is the transient plane source or TPS method. So this is the flexible double-sided sensor, conforms to the various ISO as well as ASTM standards. So this is one that we'll talk about. But another one is the TLS or transient line source. So this is a non-planar style sensor. It's actually a needle probe, which is inserted into the sample. I was kind of showing that sample prep image earlier in those slides. So the needle probe is one that does have some additional considerations on the prep side, but we do see reference to the ASTM D5334 standard for some of the concrete testing. And I'm going to kind of talk about kind of the comparing and contrasting between these two. That being said, one thing I have heard in discussions with some clients of ours, groups that are interested in testing, even in some publications that I've read, is kind of a general kind of consensus here that would say, well, TLS is better because it captures a more representative volume of this heterogeneous sample. And I wanted to take a minute just to kind of address this, if this is kind of where you're coming from, or if this is, maybe what you've been told, and kind of talk through it a little bit, because to a point, this can be true, but it's not always the case. And that's because when we talk about your evaluated volume, we have to look at your probing depth. And I'm using TPS here as the example to really kind of compare against that statement about TLS. The assumption that the TLS is basically the winner because it evaluates more doesn't hold up when you consider the fact that TPS comes in a variety of sensor sizes. By design, TPS, and actually why we relate the sample size requirements to sensor size, is because there is a requirement in terms of the measurement validation process, which is done through a series of checks, again, kind of outlined in the ISO and ASTM standards. But you have to match your evaluated volume relative to the size of the sensor. So your probing depth scales based on sensor size. So you can imagine if you were comparing a very small TPS sensor, so a 6 millimeter, or even some of the smaller, down to 1 millimeter sensor sizes, and you were to place that on, a heterogeneous material, well, then yes, a needle probe, which is inserted down, is going to capture more volume and be more representative. But through the use of the larger size sensors, you can actually, in some cases, get a larger evaluated volume than the TLS. So, that comment on TLS is kind of the be all end all more representative output, I would push back a little bit against. We actually have some different application highlights on concrete. You can find those in our tech library. There's actually one on the use of our 60 millimeter, which is a very large format TPS sensor, specifically for the testing of some of these more heterogeneous materials. Definitely worth kind of checking out. But all that being said, you still might be coming from, well, I've used TLS in the past. I think it's a better method. So I wanted to kind of show you the data and kind of give you some examples of, actual measurements on some concrete. So this was a lightweight concrete that we just had in our sample inventory. You kind of see it's, nothing too fancy, just general kind of coarse aggregate mixed into the system. And here you can see the two different setups. The TLS setup, where we had to drill, apply the grease, you insert the probe down into the sample, versus the TPS setup, which takes the two sample halves and you just insert the sensor in between to take your measurement. So we did both. And actually, when you look at the data here, the results between the two are near identical within a couple percent. The idea here is, again, by matching a size, a TPS sensor that evaluates a volume that is representative based on the scale of heterogeneity, it is essentially, I would say, a negligible difference here. Where the difference really came from was in the total prep time and testing time. I kind of roughly timed myself on how long it took to kind of prep and get one measurement done. TPS, start to finish, about 2 to 3 minutes, compared to TLS, which was significantly longer. So, when you're looking at options out there, and again, you may coming from a kind of a habitual use of or hearing of this method is maybe more commonly used, I would say there are many cases, a few ways to go about doing the measurements. I would say either one in this case, of course, are good options. It's just if throughput is a consideration for you, if you've got dozens of samples you're trying to get through, well, shaving 5 to 10 minutes off each measurement is going to save you a lot of time over the course of a week, right? So just kind of one example there on kind of, TPS versus the TLS method, in how that all plays out. Now, some of you who may be familiar with this or maybe picked up on it astutely may have noticed, well, I only have one sample, and kind of the setup I just showed with the TPS, of course, it's double-sided. You need to have two sample halves. So if you're stuck with one sample, what do you do? Is TLS your only option? And, just to kind of address that, well, when you look at TPS, yes, your standard configuration is double-sided, where you have your two samples on either side of the sensor, but there does exist a single-sided setup configuration for the TPS method. So when you're limited to one sample, there are additional basically configurations or options that you can operate the sensor with to accommodate a limited sample availability. Single-sided TPS is essentially, just like I said there earlier, it's a modification of the standard sensor with an insulative backing material. It's a really great option for when you are dealing with, again, sample limitations, as well as samples that don't test well with a contact agent. A couple of the methods on Trident, and kind of as I've shown there with the TLS, use a thermal grease or a contact medium between the sample and the sensor. Sometimes that can result in kind of changes or absorption into the sample. It can, fundamentally alter the measurement at the surface. So, using something like this is actually quite beneficial. Now, there are some limitations on single-sided measurements, specifically for insulative low-K materials, textiles. this kind of arrangement is not one that we would recommend. You get into some issues in terms of measurement bias, accuracy starting to really kind of drop off. But for something like a concrete, which is middle range conductivity, I think generally you'll see it anywhere from maybe like 0.4 ish up to like some more conductive concretes, maybe 5 watts per meter Kelvin or so. This is a great option, again, especially if you're limited on your sample volume. So again, you only have one sample, it's no problem. I actually did a test again on some, actually this was a Quickcrete sample that we kind of just made up in the lab. And I actually tested it with a double-sided configuration as well as single-sided. And basically what you can see here is, again, a very negligible difference. In this case, there's almost, again, either way would be a viable option here. You can see the TPS. This is the single-sided test jig, so you can actually get one that comes kind of pre-assembled like this. So you just drop it down on the surface of interest for measurement. So again, when you're dealing with your sample considerations, prep time versus sample availability, there are different options to look at in terms of getting you good thermal conductivity data. So, I kind of just shared a few quick examples there, but I thought maybe, again, just get some feedback from the audience at this point. Curious, how are you currently testing your thermal conductivity? Are you using some of the transient methods that we offer? Are you currently not testing, maybe relying on, technical data sheets or supplier information? Are you using the steady state instruments? Again, I'll give folks maybe another 10, 15 seconds here just to fill in some answers there, and then we'll go through those results together. All right, so kind of wrap up the poll at this point, share the results with everyone. So again, kind of a even spread, except for the fact about half of folks are not currently testing. So, if that's because you're, again, maybe just getting into this and you're looking for some options, I think you're in the right place. But definitely worthwhile. Like I've had a few, I often ask this question: are you kind of measuring directly or relying on additional, like maybe third-party information or just technical data sheet values? So definitely testing, it's something that would recommend, especially if you're actively pursuing this as an application area of interest. So hopefully you'll get some information here on what route you'd like to go following today's session. So again, thank you everyone for providing that feedback there. All right. So moving forward here, I wanted to share actually a publication result here next, because there's some interesting work being done in concrete, especially in academic sectors. And this was some work from a few years ago out of the Indian Institute of Technology, where they looked at the printability as well as the thermal and compressive strengths of some of these cementitious materials. This content here features the use of the TPS method in the characterization of their samples. But it's an interesting case because printed concrete is something that I think I've seen a few papers on this. And, I believe in the last 10, 15 years, it's really become quite more popularized based on some of the interesting geometries and print patterns that you can actually develop with some of these systems. But there's a difference in the makeup of the concrete used in these specific applications, specifically highlighting here that these mixes need, significantly more binder compared to your conventional concretes. And in this study, they basically wanted to assess whether that binder difference came at a thermal cost that they could somehow design around or mitigate through the use of different additives and fillers. So they were testing both printed and cast concretes with various additives using TPS. And essentially what they found was the thermal benefits here, and actually the benefits for them was the decrease in conductivity. So this was noted as a positive for their specific application. did come at the cost of some strength to the overall system. But you can kind of see here just a capture from the 2022 paper here, their control versus both the silica fumed as well as the limestone additive with varying amounts of phase change material introduced did have a notable impact on the overall thermal performance. And then when they actually compared the cast to the printed format, so same mix, just different, basically curing process and manufacturing path, you saw a net consistent decrease in that printed concrete sample compared to the cast one, which they related to the overall compaction density that was noted throughout the formation process. But regardless of what you are currently investigating, if you are playing around with those binders, the different fillers and additives here, those changes to your formulation or the changes to that manufacturing process can very easily be quantified through the thermal conductivity performance, as shown here with some of the data from the group out of India. Now, kind of switching here into some of those bio-based considerations, I wanted to specifically address sample surface quality because it is an important consideration with any contact-based measurement. So the evaluated volume that we talked about earlier is, a very important consideration, but it's only really, I'd say, half of the question. The other consideration here is when you're dealing with a planar style sensor like, the TPS or MTPS, your sample, although maybe generally planar, does have to be contacting the sensor enough to get a reliable measurement. And if you're dealing with something that has very large voids, large air gaps, or just poor contact zones, relative again to the size of the sensor that you're using, you can run into some issues. And actually, we've seen some really good work here, specifically with the use of the TLS, because we're not dealing with just that surface face contact. You're actually inserting it down into the bulk here. So you're kind of sidestepping some of those contact-based issues that can present themselves. And this is actually the kind of approach that was done in this paper here, from a group at École de Technologie Supérieure here in Canada, where they actually used the TLS to compare binder formulations and properties of their hempcrete samples. So for those, again, maybe unfamiliar, hempcrete, so hemp is a bio-based material source. You kind of see what it looks like here, and it kind of like it's a cultivated state, basically almost looks like wood chips. But this is something that has shown really interesting performance capabilities, not only from a thermal and like generally more of the insulation side, like the insulative performance, but also some, vapor permeability and hygroscopic performance as well. And ultimately here again, the whole idea behind using a bio-based alternative is to try to offset some of those CO2 emissions by either one, removing the requirement for some of those more CO2 heavy processes or materials being introduced. And actually also, so this hempcrete does have the ability to actually store some of the carbon in these systems. So it actually helps offset it from that side of things as well. But what they were looking for really in this study was, a low carbon binder alternative that they could use to mix their system together to produce their sample. And they wanted to see if that binder substitution had an effect on either the thermal or the moisture performance of the system. And again, all the data here was collected with the TLS on C-Therm's Trident. And what they essentially found here was they were able to source a local binder, actually a Canadian hydrated lime, and entirely replace the imported binder that was slated to be used. The thermal conductivity and the moisture buffering performance really gave essentially comparable results to what they were seeing with the more traditional binder option that they were using. So essentially, locally sourced materials without any negative impact on their overall performance. So I know everything, businesses that are running and dealing with supply chain issues, everything that's going on in the world right now, being able to pivot and test out maybe something that is very readily accessible that you hadn't used before, to replace something that you may be potentially losing access to, but making sure that you're still achieving those performance gains or thresholds of performance that you need. Again, a really great way to go about doing this testing. And again, here, the TLS, really the sensor design and the geometry, being able to pick one that really suits your samples that you're dealing with, really providing you that maximum flexibility in being able to get that data that you need. And then the last couple examples here are kind of on the impact of saturation. So the paper we just looked at, there was some testing they did on the thermal, the hygrothermal performance. But I want to share kind of two different data sets here, as it relates to materials being potentially saturated from both the curing standpoint. So, in the process of forming the samples, that water within that mixture escaping and drying out to form that final product, as well as more of actually purposefully introducing saturation into your sample, again, to represent an environment that is, again, going to mimic the in situ or in application conditions of interest. And this data set actually came from a client that sent in some samples for testing and allowed us to share the results here. But it was an interesting measurement because we got the sample received and we tested it initially, and it came in at about 2 watts per meter Kelvin. And when we did a review, it was a little bit higher than they expected. But I remember when I opened up the sample, even to the touch, it felt somewhat damp. Um, Turns out that, lo and behold, it hadn't fully cured. It actually, they packaged it so well in when they shipped it to us that it didn't have any time to dry out or, again, finish curing. So we actually waited a week, and tested it later. So same sample, same sensor, same system. What changed, though, is the fact that it had time to actually fully cure and dry out. And we saw a shift here of over 20% in the thermal conductivity. So these samples were sent from Rock Road Farms. Actually, it's a bio-based concrete, which with an interesting algae additive. So it's an interesting sample to measure, but it really just kind of illustrates a couple points here. Is one, when you're looking to develop your testing protocol for your materials, either looking and fully ensuring that the sample have cured before you do your QA/QC test to put out a certified value on the material. Or you could even look at it from the fact, well, you could actually measure at different time intervals to actually track the essentially curing through the thermal conductivity. So being able to assess that impact from these types of measurements, again, just gives you more insight into how your material is performing. And of course, making sure that it's in the state or the condition that you want it to be in before you go and do your official measurements. Now, this example here, again, it's on a sample that we, purposefully saturated. So we basically took a sample, concrete sample, soaked it for 24 hours, took some measurements, and then dried it out, measured it once it had fully dried. And again, similar idea here. You're going to see the saturator, that the contribution of the water in the system is increasing the thermal conductivity. Here, just shy of 2 times, or a 2x difference between the two. And again, here, the level of saturation, and the impact that it's going to have on the material will have a correlation to the structure of the sample, the porosity, how much water it's able to hold, and things of this. But again, just being able to mimic this type of condition is something that, again, could potentially be quite influential on the overall performance of the materials that you are looking to introduce. Again, maybe some of these bigger constructions where you might be going deep into the ground. Is it going to be in contact with any type of water ingress? How is that going to impact the long-term stability or performance of the systems? things of that sort. So again, just being able to test that is going to be potentially quite important. So when it comes to controlling your testing environment, I mean, these are by no means all of the options, but I just want to flag a couple of them. From C-Therm, we have a automated thermal control system. So it allows you to actually set up your samples in a controlled heating environment using our dedicated furnace and thermal chamber. As shown here, there are other options that exist, but this is our newest, basically thermal control option that we've recently launched. Also, we've had some requests to actually specifically test samples inside of a humidity chamber. Again, kind of that, if you're to saturate the sample and maybe you wanted to do some long-term testing and you didn't want it to dry out and maintain a certain level of saturation, actually putting the sample in a environmental or humidity controlled environment can also be quite relevant. And then, I mean, we could talk about all the pressurization options and things of that sort, but these are two that we've seen potential interest in this space, and just wanted to share a couple of those different off-the-shelf solutions that we can provide to help simplify your testing process. So in terms of kind of summarizing today's content, really, I'd say three main takeaways here. As we kind of highlighted at the beginning, your two most common options here are TPS and TLS, both viable options for concrete, but really they differ in terms of how much prep is going to be required. When it comes to the TPS, again, if you only have one sample, it's fine. We can test in both double and single-sided configurations. So, if you're limited on the volume of materials that you can produce, but you still want to use TPS, there are pathways to accommodate that. And then through all the different data examples, the publications here, the formulation questions really can be tied directly to those thermal questions and considerations. So whether it's the binders, the additives, looking at bio-based systems, the curing conditions, all of these factors are measurable and quantifiable through thermal conductivity. And again, depending on which path you're looking to go, can be quite simple to actually get that data collected and get insights on your material performance. So kind of wrapping things up before we go and kind of finalize and move into the Q&A. One last poll, and this one will remain anonymous for you, but just wanted to get some feedback from you, always trying to help improve. Just kind of very short answer here, but how would you describe today's presentation? Anything that you potentially might want to see more of in the future, just feel free to type some answers in there. And this will be kind of reviewed by us internally as we plan our next sessions going forward. So thank you very much for the feedback here. Awesome. Okay, so a good amount of folks have answered, so I'll go ahead and close this out in a few seconds here. All right, thank you very much. Right, so yeah, just kind of wrapping things up here today. Just wanted to leave everyone with just a few kind of what options you have in terms of next steps and how we can support you. So Thermal Analysis Labs is C-Therm's contract testing division. We offer all the methods available on the Trident system, as well as other methods in industry for thermal conductivity and other related properties. If you are, amongst the group of folks that answered earlier that right now you're not actually testing your materials, but maybe you're looking to take an initial step and kind of see what the data looks like, our testing division would be more than happy to kind of have a consultation with you, discuss your samples, and provide you some testing options. I actually wanted to share, this is a recent testimonial from one of our TAL clients who was working in the concrete space. Got a note they were working on testing thermal conductivity of concrete, looking at specific cure times. But I just want to highlight this because it really, I think, embodies what TAL does. It's not just testing your samples and sending you a report. We do really pride ourselves in being able to really scope out, taking that initial review with you, make sure the scope of work is aligned, anything through special sample prep requirements you may have, of course, the testing and results. and the follow-up. We will always be there to do a data review. If you want to discuss the results, maybe bring in other stakeholders that need this explained to, we're certainly happy to help in that context. So here, this quote testimonial from Ultrabiota, just kind of introducing their experience with us. And again, just wanted to put a few images here because over the last few months, whether it was through our TAL testing division or through some of the instrumentation discussions I've had with clients, these are actually some of the I'd say, three core areas of application that the concrete work has been focused on. Some AI data center groups, bio-based, and just general concrete testing. Over the past, again, few weeks, there's been quite a few inquiries and tests that have been run here at C-Therm to kind of cover these sample types and applications off. So if you're dealing or you're working in this space and you want to chat, we'd be certainly happy to accommodate. While it wasn't the focus of today's discussion and related to today's application, I will just always reference our partnership with ZFW for their line of TIM testers and high temperature heat flow meters. This, again, wasn't really the kind of fit for today's application topic. However, if you are dealing with a variety of other material types, maybe more traditional thermal interface materials or insulations, high temperature requirements, we're certainly happy to offer up some opportunity to chat about both our transient solutions as well as the steady state options. And with that, coming up to the end of today's session, I'd just like to take a moment and thank folks for your participation, joining today's webinar. We'll be transitioning here to the Q&A in a few moments. But for the folks that are hopping off, once again, thank you for joining, and hopefully we'll see you around at one of the upcoming events.